Okay, good afternoon, folks. Is everything okay? Do you see the image and also the sound is good or everything is okay? Good, thank you. Okay, your second midterm is going to be on Wednesday or Thursday, depends on when your discussion sections are. And um, I will, I wrote your midterm exam. It's going to be 9 questions as I send you guys an email and explain about the midterm exam. So it's going to be from chapters, I don't remember exactly, I think chapter after 8, all the way through chapter 18, but not including types of errors that I'm going to cover today. And uh, um, the exam is going to be difficult or challenging, more challenging or more difficult than the first exam. Don't take it easy. Don't take it slightly lightly. Just thinking that, oh, it's just a finding average or standard deviation or such and such. That was in the first exam. This exam is a little bit challenging. If you know the subject matter topics that I covered in terms of the null hypothesis, confidence interval, and the kind of things that I put on review questions without looking at the solutions. If you can solve those, go through those questions, then you're going to be okay. I mean, you might have a few more challenges too, but overall you'll be okay. But if you're having problems understanding why things are, what I did in the review questions in terms of answers, and you don't know how to get those things, you need to study and understand the topics. And again, the final exam is going to be more challenging than the second midterm exam. So you need to be prepared. This is the first time in the last 2, 3 years I've been teaching this course. I'm warning my students. I usually say that, well, they're adults enough, they know what to do. But usually, my previous experience showed that students get, when they see that their grade goes down because either they think that it's going to be as simple as the first midterm exam and they found out no, it's not, or or they don't study hard. So I highly recommend that take it seriously. And if you have questions, please see me or see one of the GEs. You still have time to things that you don't understand. Well, ask questions. Anyhow, that was my recommendation. And if you don't have any questions, I'll move on and then cover the rest of chapter 18 and then move on to chapter 20. And your Excel program is the next one, Excel number 5 is going to be on. You can open it at 6 o'clock today. I purposely made it instead of 2 problems, I made 1 problem. So you don't have to spend too much time on doing the Excel. I mean, it's easy, you can do it, but I purposely did that so you can spend time on working on your midterm exam. That was the reason. It's 1 problem. It's 15 points. Okay, let's get started. So we are still talking about confidence interval and also tests of significance. And we got to the point that we have 2 types of errors. So we're going to talk about these types of errors and the power. That's the rest of this chapter, chapter 18. So, by the way, you're okay with Excel that last time I explained it, explained to you guys on piece of paper. I wasn't able to go to Excel and show it to you guys. Are you okay with that? That how to calculate the Z star using Excel? It was really straightforward, but my software wasn't, updated. So you're okay with that? Then I don't have to go through the Excel. It works fine, Jane. Okay. So you guys are okay then? Excel was good. 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 I'm glad that it was good then. So you don't need, you don't want me to go there. Okay. So we have two types of errors. One is called type 1 error and type 2 error. So these types of errors is basically the definition. You got to look at the definition, what the definition is. So the definition for type 1 error is basically we reject H0, null hypothesis, but in reality, actually, null hypothesis is the correct answer. So this type of error, we call it type 1 or false positive. And the significance level alpha is the probability of this type. So if alpha is given to you, basically that's going to be the probability of this kind of error, to see that kind of error, meaning that you're going to reject the null hypothesis, but in reality, null hypothesis is the correct answer. That is the error. And in general, for type 1 error, we have false positive, then this means that we reject the null hypothesis, rejecting the null hypothesis, which is H0. And that means rejecting this, but we know H0 is correct, is true. That is basically type 1 hypothesis. Alpha, and we use alpha, which gives us the probability of error. Type 1 error. Type 1 error. Okay. Type 1 error. And type 2 error is the other way around. That means, so we fail to reject the null hypothesis. So if you fail to reject the null hypothesis, that means you accept the null hypothesis. Therefore, you reject the alternative hypothesis. But in reality, actually, alternative hypothesis is the true one. So it's opposite to what you have. Now, this is called type 2 error or false negative. That's a definition, basically. So basically, I'm going to write a type 2 error. And here you have, we call this one false negative. And we say fail to reject the null hypothesis. In fact, in reality, we know that knowing that H0 is true, the null hypothesis is true. Knowing that alternative hypothesis is true, not the null. Alternative. This is alternative hypothesis. Okay. And here the next thing is those are the errors. And the next thing is the power of a test. And usually when you do the power of a test, this is against the alternative hypothesis. You do this power of a test against alternative hypothesis. All you're saying that we reject the mu0, which is a null hypothesis, and we want to know that what's the probability of accepting the alternative mu, which is in this case mu a. That is the whole idea of power of a test. It's always against the alternative hypothesis. You want to find the power. So is the probability that we reject the null hypothesis when it's false, and the probability will correctly claim mu is really equal to mu A, not mu 0. That means you rejected mu 0 and you want to say what's the probability of accepting mu A. So basically, here, consequently, the probability of type error 2 is 1 minus 1 minus power. Remember, type 1 error, the probability goes to alpha, the p-value that you have. Type 2 error, the probability is you calculate, you take 1, and you subtract the power. And this power is, we'll do one example, you can see what it is. And this power is basically you're looking at against the alternative hypothesis, and you want to see the probability of mu sub A is happening and not mu sub 0. Mu sub 0 belongs to the null hypothesis. Mu sub A belongs to the alternative hypothesis. You're looking at the probability of that. Okay. So, so this is nothing but basically you're looking at, this is the power of, you're looking at the error. The error, that means when failing to reject H0. That is the error, not the power. Power is rejecting that. The power is basically rejecting H0. 1 minus rejecting that, it's going to give you failing to reject H0, and that would be the error that you're dealing with. So another way of saying it, power of a test, we say HA sub A is true, and H sub A is true. Whatever the mu is, it could be we are accepting mu A. It depends on the condition, whether it's greater than or less than or not equal. Okay, that's a definition. Let's see one example. Okay, this is example 6. A hypothetical study on fibromyalgia treatment reports that at 1% significance, so that would be alpha, 1% significance now. Alpha is 1%. Okay, so we are looking at this problem, 1% significance, and against alternative hypothesis that the experimental drug reduces pain by an average of 2 units. Put units here. It's a subjective matter, so I'm going to put units. On a subjective pain scale, the test had power. This is what we have. Power is 0.88 or 88%. So what does this mean? That it's basically the alternative test has a power of 88%, rejecting the null hypothesis and accepting the alternative one. That means rejecting the mu 0 and accepting the mu sub A. 88%, that's the power. Okay, so what do we have here? It says A, what is the implied value of mu 0? So we know that H0 is, we're talking about mu 0. If mu 0 is equal to 0, that means no pain. That means no reduction of pain. No reduction of pain. That is the null hypothesis. That means you don't want to see any differences and you go with the most conservative situation. So in this case, null hypothesis, there is no reduction of pain. Okay, now what is the probability of type 1 error? What does type 1 error mean in the context of this experiment? We said that type 1 error goes back to alpha. If alpha is 1%, so that's equal to 0.01%. So that would be equal to type 1 error. Okay. Now, what it says, what does a type 1 error mean in the context of this experiment? It means that 1%, if this is the error, for error type 1, that 1%, the chance of reducing pain is 1%. That's what it means, basically. But in fact, it doesn't reduce pain because based on the probability what we have. Maybe we can say there is a 1% chance that the drug does reduce pain level, and so basically rejecting H0. When in fact it doesn't reduce pain. Okay, that's type 1 error. Type, let's see, describe as though to someone with no statistics experience what the power of this test mean. Well, assuming that based on what this says here, the problem says the pain can be reduced by 2 units, right? If we use the experimental drug, can reduce by two units. That reduction of 2 units can happen with the 88% probability. That's what it means. So based on what we have here, it says the experimental drug reduces pain by an average of 2 units on a subjective pain scale. So that means the chance of reducing 2 units of pain on a pain scale is 88%. That's the power. So what we can write here, assuming that the treatment actually reduces pain by 2 units on the pain scale. That means this is basically there is an 88% chance that we will reject the null hypothesis, H0. And correctly say that the drug works. That's the power. Definition of the power. Now, type 2 error. What is the probability of type 2 error? Remember, from the previous thing, we said that type 2 error is 1 minus power. So let's just fix my laptop again. Okay, type 2 error means that, so we have to take this power that we have here, 1 minus that power is going to give you type 2 error. So one minus power, and that would be 1 minus 0.88, that would be 0.12. So basically, this is the error now. So we can say there is a 12% chance that there really is a 2-unit reduction, but our sample convinces us to fail, to reject the null hypothesis, HC. So basically, when you have this error is going to say that we can't, 12% chance that we can reject H0. That's what it says, basically. All right. So those are types of errors and power. And we are done with chapter 18 now. And again, questions regarding today's lecture, it's not going to, these questions are not going to be, these topics are not going to be in the midterm exam. These are going to be in the final exam. All right. If you don't have any question, let's move on to chapter, the next is going to be chapter 20. Chapter 20 is basically this chapter. Okay, so type 2 error goes against the null hypothesis as power agrees with, no, the power agrees with the alternative hypothesis. Power is always against alternative, and it says that how accurately the alternative hypothesis is going to happen, the alternative. It's going to reject, basically, it's not accepting mu 0. So it's accepting mu sub A, which is saying that 2 units of pain reduction. And 1 minus that, that's the error. It's telling us that, oh, maybe we should fail to reject the null hypothesis by the error of 12%. Okay? That is the error. 12% is the error, and 88% is accepting alternative. Okay, let's go with chapter 20. Chapter 20, so far, you know, we want to continue talking about population mean, mu, and what we want to do to change our condition basically is to be more realistic. Look at more realistic things. So far, things are not realistic. Basically, it's nothing but more ideal case. Like, for instance, we had the standard deviation of the population. We really don't have that unless, you know, we just do go and ask, I don't know, so many million people and find a population, find the standard deviation. So in order to make it more realistic, so we say that, like in previous chapters, we always use Z procedure, and we talk Z procedure, we talked about the confidence interval, test of significance, but for all these cases, we already knew what sigma was at that time. Now we are going to relax this condition, and we are going to say that we are going to do things more realistically, meaning that we assume that sigma is unknown. The minute you say sigma is unknown, your distribution goes from Z distribution to T distribution. And we'll talk about this. So again, we are going to use similar methods, but there's going to be there will be some differences. You're going to see that along the way. I will explain those differences. So the conditions of confidence intervals and tests of significance will change only slightly because we don't know what sigma is. And the important point is that the result that we get, we are going to do the same kind of, we are looking for the same kind of results. That means p-value. We are looking for p-value. P-value is going to be the probability of accepting or rejecting something. Okay, so we are going to base on X bar, which is going to be the mean of the sample. And you're going to see there's going to be a lot of similarities between T distribution and Z distribution. The main thing is when we do with the inference, and we have to observe that it's SRS and also normal population distribution. And in this case, we say sigma is not known. So let's go through this and see. We're gonna look at some definitions here, and then we move on from here on. By the way, this is one sample t-test. You're gonna have two sample t-test 2, and then this is dealing with the population mean, assuming the sigma is not known. And from here on, we have, I think after chapter 20, we have 3 more chapters to finish, 3 or 4 more chapters. So it's basically sigma is known and unknown, 1 sample and 2 sample, and that's going to be it. So you're going to see more formulas, a little bit more complicated formulas when we move on towards the end of the term. Okay, the 1 sample t-test, again, let's look at the definition, is a confidence interval or significant test for mu when sigma is unknown. And again, guidelines are, we want to have SRS, and we want to know the distribution is normal. And I would put, and rather than sigma here, I would put it here, sigma is unknown. It's there, but it's if you want to put among the conditions for the t-test, that's going to be the case. I'm going to draw 2 cases. One is, I'm going to show you one with the Z distribution, compare 2 things, Z distribution, and this is going to be T distribution. We're comparing those 2. In Z distribution, I need to have X bar. Also, I need to know mu. Oops. I mean, those are the components that I'm going to deal with. Mu, sigma is known, n is the sample size, Z star is the critical value for Z distribution. And here on the T side, we have X bar, mu, sigma, no, we don't know sigma. I'm going to cross it, I'm going to write it there, but cross it out to show you that this is not known there. Instead, we know S. This is the standard deviation for sample. You have standard deviation for sample. N is the sample size, and T star is the critical value of T star. It's a critical value, has a critical value. It's like similar to Z star. Here we use table C In this case, we are going to use table C, but table C, it's not the same as you're going to see that we have a T and we have a degrees of freedom and things, other things. On the Z distribution, we have CI, confidence interval. If you recall that, it is X bar minus Z star sigma over square root of n. That is the lower end of that. The upper end or higher end would be X bar plus Z star sigma over square root of n. For the T case, for the T distribution, confidence interval is X bar minus T star instead of Z star. Instead of having sigma, because we don't know sigma, we are going to put S there, square root of n. And this would be X bar plus T star S over square root of n. Okay. In this case, Z statistic is Z is equal to, it's X bar minus mu divided by sigma square root of n. On the T distribution, we have T is equal to X bar minus mu divided by S, not sigma, square root of n. This is at the bottom, the denominator. Also, one extra thing that T distribution has that Z distribution doesn't, that is called degrees of freedom. And that is equal to sample size minus 1. So this is called degrees of freedom. Okay? So when you look at like a 90% confidence interval, so for this one, it's going to be something like that for Z star. So that would be 90%. For T star would be elevated. You're going to see that why it's elevated. It's going to be something it's similar. The only difference is here it's much fatter compared to here. Here you see how small it is. And here is, again, for this one, if this is the 90%, that would be the 90% of the area. The thing that you want to pay attention, here we have 5% on this side, 5% on this side. Because this thickness is much smaller, this tail goes way all the way out here to cover that 5%. But in this case, since it's thick, it stops at that point because this is the area of 5%. Those are the things that you're going to see the difference. And here we are going to use this degrees of freedom. I want to show you on table C. This is, see that? Here it says degrees of freedom. So if the sample size is, I'm just giving you an example, 15, degrees would be, if sample size is 15, degrees of freedom would be 14, and you're going to look at this row with this confidence level, and then you find that T star. Okay? Suppose you're looking at 95% confidence interval with sample size of 15. Sample size of 15, you're going to subtract 1 from that 15, and it's going to be 14. 14, you go on this line and go up 95%. That would be, T star would be 2.145. Okay? Versus Z star, if you would have looked at the Z star, you come down all the way, that would be 95%, that would be 1.960. That's a difference. Okay, we'll do more. We'll do some examples, and you can see what they are. All right, let's move on. Here we have definition. The standard error of a statistic is the standard deviation of the statistic estimated from data. That would be S. The standard error of the sample mean X bar is S divided by square root of N. So basically what we write, standard error SE. They're going to see that that's SE, and that's equal to S divided by square root of N. This is the standard deviation of sample that we are dealing with. And this is the sample size. Okay, let's do one example. Let's do it together. So we have example 1. Find the standard error of X bar. This has an X bar. Given the simple random sample chosen from a normal distribution. So if I want to find the standard error, what do I need? Okay, I'm going to rewrite it. Standard error is equal to what? It's equal to standard deviation divided by square root of N. 1, 2, 3, 4, 5, 6, 7. So N, I know N is 7. But I need to find standard deviation. So in order to find standard deviation, I need to know mu. Remember, the formula for standard deviation is what? If you recall that, let's call this one x1, x2, x3, x4, x5, x6, x7. So if you want to find the standard deviation, if you recall that standard deviation is equal to 1 divided by n minus 1 times, you recall that it's X bar minus X1, the whole quantity squared, plus all the way X bar minus X7 squared. That was the standard. And these dots mean that it's going to be another one. You have 7 terms, you know, with X1, X2, X3, X4, all the way to X7. So that's a standard deviation. So you notice that if you want to calculate this, this is a kind of a review. This is from the first few chapters. So if you want to find X bar, the standard deviation, you need to know X bar. So X bar would be first, you got to add these numbers, 53 all the way to 45 divided by 7. And I've done this, this is 38.7. That is X bar. Now, knowing the X bar, now we want to find standard deviation. Standard deviation is equal to 1 divided by the number of data points is 7. 7 minus 1. Then I got to put it in the bracket here. So we have X bar is 38.7 minus X1. X1 is minus 53. The whole quantity squared. The next one again, X bar, which is 38.7 minus X2. X2 this time is 20 squared. And you do all of them all the way to the last one. That would be 38.7. That's X bar minus X7 is 45 and squared. The whole thing is squared, and you do this. So put it in your calculator, just subtract this, square this, subtract that, square that, and then add them up. And this is going to be 6. Notice that everything here, even if you subtract from here, when you square it, everything is positive because square of negative number is always positive. Again, I've done this standard deviation. We call this standard deviation. let's use the same notation that we use for here. Standard deviation is, what is it? I calculated it's 17.4806. Okay. Now I have the standard deviation, and also I can calculate now sample error. What would be the sample error? It would be S, which is this one, 17.4806 divided by square root of, and that would be square root of 7. And if you do that, the error becomes 6.607. Okay. All right, let's move on if you don't have any questions. Okay, this is like we have, remember we had Z statistic. This is the similar to for the T, the variable we use it. T statistics, test statistics for T. Here we have the test statistic T for a normal distribution. This is for T. We are doing it for T with unknown mean mu and sample standard deviation S taken from SRS size n defined to be that. I'm going to show you, I'm going to put the Z part here. Z is equal to X bar minus mu sigma over square root of n. This is the Z. This is the counterpart of Z, which is T. Okay. Now we say T has T distribution with n minus 1 degrees of freedom. Remember, n was sample size. Degree of freedom is n minus 1. That's what we call it, n minus 1 degrees of freedom. And also we can, another symbol we can show it, it's either T n minus 1 or T sub n minus 1. Those are the notations that we can use. I want to draw something and show you the similarities and differences between Z distribution and the T distribution. So let's see. Let's start. This is Z. Now it's very narrow here, and it goes all the way here. That's the mean that you have here. In this case, if we go with the Z, that's mu equal to 0. The standard distribution, normal standard distribution. Now, if I do, I'm going to use different color, and I do, so I'm going to do for the T distribution. So it's going to go like that. And I'm going to assume that this is like for T4, maybe. So that means this is sample size 5. This is T4. Degrees of freedom is 4. If I increase the degrees of freedom, what happens, this will go down, this will come up. It becomes like this. And this is suppose say, I don't know, T9, 10. I just want to show you the difference, what happens. Now, if you increase degrees of freedom, go to infinity, it becomes a Z distribution. The more degrees of freedom you have, the closer you're moving towards the Z distribution. In terms, you can see it in the curve here. This is T4. This is T4. You can see this part, the tail is much fatter than what we have for the Z distribution. But if we go to T9, you can see that this is getting narrower here, and this is getting closer to this. If T goes to infinity, basically huge degrees of freedom, this becomes a Z distribution. Okay? Okay. Now, the L an L level confidence interval for mu is given by x bar plus or minus T star S over square root of n. This was for T. For Z, I'm gonna, if you recall that for Z, we had it x bar plus or minus, and we had Z star, and then we had sigma over square root of n. This is for the T distribution. That's for the Z distribution. Okay, now it says where the observation, as we said, that conditions is SRS, a normal distribution, n is the sample size, T star is the critical value, the same as Z star was a critical value, in the Tn minus 1 degrees of freedom. In the Tn minus 1 density curve with the L between minus T star and plus T star. Remember, we had a similar situation. Here, we called it Z star and minus Z star. Here, we call it T star and minus T star. It's the same thing, same idea. Okay? And now, use table C to find these values. So we are going to use table C to do. Let's go with an example. I'm going to give you an example. Let's say example is we are looking at a sample size, I don't know, 12 maybe, n is equal to 12. And say confidence level, say we're looking at for L to be confidence level should be 99.5%. 99.5, yeah. 99.5%. So first of all, from here, we know that degrees of freedom would be n minus 1, and that is 12 minus 1, that is 11. That's degrees of freedom. Now, we want to find the T star. If I want to find the confidence interval, in confidence interval, I need to know what T star is. So in order to know that, so I need to look it up. So what I'm going to do, I'm going to show you something on the table here, and then come back to that sheet and draw something that you can remember. Okay, so we learned that our degrees of freedom is 11, so that would be degrees of freedom. Remember, the first column is degrees of freedom. You can see it here. And the other one is 99.5. That would be 99.5. So this would be 3.497. 3.497. From here, not from here, from 3. Let me just remember, 497. So basically, from degrees of freedom 11 and these two, we get this one, which is going to be T star. Now, what I'm going to do, I'm going to draw the picture a little bit here. Suppose this is the column, the F column. And suppose this is the DF column. Maybe I should do it this way. The F column. And this is the confidence level. So here we have 99 99.5% column. You have other numbers there too. Here you have numbers, then you get to 11. So you go from 11, this row, drop a line here. Whatever the number you see here, in this case, we saw this number over here is basically 3.497. And that is your T star. And this is equal to T star. Now, knowing the T star, you can find confidence interval, and that would be X bar minus T star S over square root of N X bar plus T star S over square root of N. That's how you find T star, and then that's how you're going to end up calculating confidence interval. Okay? Let's do one example again. Example 2. Example 2, it says find the 96% confidence interval for the mean diameter in centimeters of snowflakes given the following SRS. So we have SRS, this is that. Here it seems reasonable to assume that the data comes from a normal distribution. So you have this value. How many do we have? We have 5, 10. Sample size is 10. The degrees of freedom would be 9. 10 minus 1 is 9. Okay. Now, if you want to find the confidence interval for this, find the T star for this. So we got to go and look at the number. Degrees of freedom is 9, and confidence level is 96%. So if you do that, again, this is the table C. That would be 96%. Is it 96? Yeah. 96%. And we're going to look at row 9. That would be that number. This is 9 degrees of freedom. And that is 96% confidence level. So the number T star would be 2.398. 2.398. From here we have T star is 2.398. Table C. Using degrees of freedom and also confidence level. So we have that. And the rest is, again, obvious, it's the same thing. Again, you're going to put x1, x2, all the way here. And this would be x6, all the way down here, x10. So what do we do first? We got to find x bar. So x bar is equal to, that would be 9.34 all the way to 7.27 divided by 10. And if you do that, you get 5.28. 5.28. And then you have to find the standard deviation. Standard deviation would be square root of 1, n minus 1. Then you have to write x bar minus x1 squared all the way to x bar minus x10 squared. And if you do that, standard deviation would become 10. That would be 10 minus 1. That's 9. And you put these numbers there. The first one would be x bar is, we calculated x bar is 5.28 minus x1 is 9.34 squared. You do all the way to the end. Notice that This entire thing is multiplied by 1 over 9. The last one would be 5.28 minus x10. X10 is 7.27 squared. And if you do that, which I did it, the answer is 2.258. That's the answer. So now we have S, we have T star, we have the size, and we have the X bar. So we should be able to write confidence interval, and that would be X bar minus T star S over square root of n, X bar plus T star S over square root of n. So confidence interval is equal to X bar is 5.28 minus T star, it's 2.398 times S, we calculated is 2.258 divided by square root of n. N is 10, number of data points for the sample. And we do the same thing, just change minus to plus. 5.28 plus 2.398 times 2.258 divided by square root of 10. And if you do that, I got the answer to be 3.5677, 6.992. That is the confidence interval. For the t distribution. That means we didn't know anything about sigma, but we used the sample and we calculated and we got that answer. Confidence interval. Okay. All right. Let's move on. Here we have robustness. I mean, what is robustness? Robustness is something something happens out of the blue and your system resists. It doesn't get destroyed. It doesn't have any effect on the results, or the effect is very small. So you say that system has robustness towards that, whatever the factor was, that unpredictability, that something happened to that. Okay, so that is what we call robustness. Here, robustness is the ability of a test to still be valid despite having at least one of its formal requirements changed or removed. Something disastrous happens, for instance. Like you build engines for cars or airplanes, right? So if the airplanes or cars are made for the US, and so they work here. But if the system is robust, that means cars and airplane engines, when you take them to places really cold like Siberia, North Pole, South Pole, if they can resist there, they can fly those airplanes with much lower temperature, then you say their engines are robust because they are operating normal, okay, despite having something abnormal to them. That is a robustness. Now, this test that we are dealing with, it has robustness provided that these are the definitions. These are the things that you got to remember, write it in your note card in the final exam. So these are going to change for different cases. Like in this case, for one sample t-test, we are doing it for this robustness. Again, the assumption is you have SRS. Most of the time, almost every time, you should have SRS. Okay, now if your sample size is less than 15, you're taking a sample from the distribution, and you want to do the t-test, that means you don't know the sigma of the population, then if the data appears to be close to normal, symmetric, and no outliers. So if this is the case, yes, this is still acceptable. If you have outliers for n less than 15, it's not robust. You won't accept it. But if this is almost normal, almost symmetric, and you have no outliers, then it is t-test, it's acceptable, provided that n is less than 15. The second case is basically if n is between 40 and 15, you can use the t-test, and if the data has at most slight or moderate skewness, it's okay. If it's a little bit skewed, even if it's not symmetric like we had there, because we had fewer data points here. Here it's okay. Even if it's a little bit skewed, you can still use t-test. The last one, if n is greater than or equal to 40, then you can use t-test for any distribution. Skewness, it has, not symmetric, whatever it is, you can still use this one if the size is greater than 40. Okay, let's do example 3. Example 3 is, it says, it is suspected that the type of terrain can affect the current of a lightning bolt strike. Basically, you're looking at that. At a particular location, the average current of a lightning bolt is 10 kiloamps, 10 kiloamperes, 10 kiloamps. A random sample of 4 strikes at a site with lower mineral content yields currents as follows. These are the currents for that. Basically, it's kiloamps. We usually show it with Ka. That stands for kiloamps for each current. Why do you think the sample size is so small for this experiment? Why? Because lightning can rarely hit the same place more than once. Rarely can happen. So that's the reason the sample size is small. Even if you go for the vicinity of this location, you pick a location, you go several miles away from that, but still the likelihood of hitting the same location or close to that location, it's rare. So basically lightning strikes particular location lightning strikes a particular location could be rare, relatively rare. Okay. That's page 3. Go to page 4. Okay, before I forget this, I gotta remind you that there is gonna be review session by Ross and Christoph, and that's gonna be tomorrow from 4 to 6. And I believe the room was in DD Hall. I don't remember exactly because I have 2 classes and I have 2 review sessions. I don't know which one is which, but I send you guys an email, and if you don't have the email, you can actually go to Canvas and check it out. It's there. All right. Now back to this problem. Is there a significant difference in current between the sites? Okay. Now we are back to null hypothesis. This is what we have to do. But here we are using the t-test, t-distribution. So what we have here, so we are going to say, let's just look at this way. Here what we have, let's go back. Do we have an, yes, we do have an average. That's the mu zero. This is the mu zero is 10 kiloamps. Okay, so we have here, so H0, null hypothesis, that would be equal to mu zero, where mu zero is 10 kiloamps. Okay, so we can rewrite this one as like a H0 to be mu equal to 10 kiloamps. That's H0. On the other hand, the alternative would be, it says, is there a significant difference? It doesn't say smaller or greater. Difference. That means H sub A, mu of alternative has to be not equal to 10. Because it says difference. It doesn't say smaller or greater. So it's 10. We know that the sample size is n, 4. Therefore, df would be 4 minus 1. That is 3. What else do we want to know? That's it, I guess, right? So we need to find x bar, whether you want to calculate for confidence interval or test of significance, you need to know x bar. So x bar is equal to, you have 4 data points. That would be, x bar would be 9.93 plus 13.67 plus 15.01. Right, we're looking at the data points plus 11.92. There are 4 of them divided by 4. And if you do that, you get the value 12.6325 kiloamps. We got that sample average, basically. Now, the next thing is, we have that. We need to know standard deviation. Again, standard deviation, n minus 1, I'm going to write the formula there. 1 minus 4 times, again, it's going to be 9.93, or x bar minus, it doesn't matter, because you're squaring it. 12.6325 minus 9.93 squared. We do all the way to the last one, and the last one is 12.6325 minus 11.92, square it. And if you do that, this becomes 3. And if you do that, you get the standard deviation to be 2.20152. That's the standard deviation due to the sample. All right, now let's find the t-value. T is equal to, we call that T is equal to x bar minus mu divided by S divided by square root of n. X bar, we already calculated. Where are we? Here. 12.6325. Mu, we said, is mu 0 is the same mu, this is mu 0, minus 10, divided by S, we calculated to be 2.20152, divided by square root of sample size is 4. And if you do that, you get the t-value to be 2.3916. Okay. So let's look at this. Now you have Z value and degrees of freedom, right? My, what is it? What do I have here? I have degrees of freedom 3. That's the way we are going to find confidence level. That would be 3, right? Because that is the degrees of freedom 3. And we are going to get as close as possible to that number. The number is 2.3916. 2.3916. So it has to be between these two numbers, right? 39. So it's very close to 90%. You see that? Because the other one is 3 point. It's not 2 even. So we are going to go with this one. To be on the safe side, we say it's 90%. So from here, confidence level would be 90% or 0.9. So if you plot this, this is going to be, remember we're dealing with the t distribution. And here, this is going to be 90%. And this area would be 5%, and that would be 5%. So what did we say about alpha? Alpha is equal to 1 minus confidence level, and that would be 1 minus 0.9 is equal to 0.1. And if we would have gone with the 95%, that would have been 2.5 here, 2.5 here. This would have been 0.05. And we can do it that way. Let's just do that one because the number was exactly between those two numbers. Let's do, if you go with the 3, the other one would be 95%. 395. That would be 3.182. 3.29, that would be 96%. So then I have another 95%. Then I have another one. Again, so this would be 2.5%. That would be 2.5%. So alpha for this one would be 1 minus 0.95. That would be 0.05. So p-value due to this one, p-value due to this one, it has to be 0.1 or 10%. P-value due to this one, the next one, it's going to be 0.05 or 5%. Okay? So in general, what we can say the p-value lies between these two values. It's less than 10% and greater than 5%. Now, is this a significant difference? If p-value greater than 5% and less than 10%? Well, it's not a great thing to, it's not a great value. It's just a value we usually say that it gives us to reject the null hypothesis, because we usually assume that things should be less than 5% to accept. But this is the p-value. Okay. Part C, why should we be concerned about the validity of our significant test? Why? Because sample size is 4. Small, very small. Remember robustness, when we talk about the robustness here, if it's less than 15, that means t-test appears okay, but you need to have normal, symmetric, no outliers, and so forth and so on in order to say that you can use distribution, t-distribution. So if I rewrite that, that would be lightning current lightning currents lightning current distribution should be close to, because it's less than 15, you want to have it as close as possible to the normal distribution. Normal distribution, and you don't want to have no outliers and no skewness. Almost symmetric is good. You want to have symmetric. If these conditions meet, then we say, so the t-test is acceptable. You can use the t-test. Okay? All right. Page 5. So this is another example, example 4. And this example is, it says, evaluate the hypothesis that alcohol increases the time before responding to stimuli. Subjects are given a moderate quantity of alcohol and then instructed to click on a button after seeing a particular image. The average response rate for the population of sober individuals is 220 milliseconds. For a particular motor skill test, that is what similar to that. On the same motor skill test, the SRS of 50 subjects provides a mean response rate of 226 milliseconds with a standard deviation of 16.5 milliseconds. Okay, so we want to do what we want to do here is to calculate again. We're going to find mu zero, null hypothesis, and so forth and so on. But before I start working on this one, I just want to say something that if you're using Excel, in Excel, you have t distribution too. So you use t.dist there, and there you have x here, df here, degrees of freedom you have to put, and you always put that 1. And also you might have t.dist this way, x, df, and tail. Tails is you have one tail and two tail. We talk about this later. Also, the inverse of this is going to be, of course, you have to put equal sign. The inverse of this, that would be t dot inv. And this would be, again, t dot, or you have t dot inv, and you have one t, no, this is inv, no dot. You have two of them. Okay, oh, okay. I guess we are done. Good luck on your studying for the midterm exam. Where is my phone? I can't find my phone. Okay. What sections will be in the midterm? I sent you guys an email. It's on Canvas. It's there. The sections I wrote there, everything is there. You need to check your email and also check. Where is my cell phone? I don't know where I put them. It's just anyhow. It's on Canvas. You go to Canvas, and It's there, and you got it in an email too. No, today's in won't. I said that. No, today we talked about the errors and chapter 20. In that email, I specifically said that what chapters are going to be on the midterm exam. Okay? Are we good? All right. Good luck to you guys. If you have questions, contact your GEs and myself. We can help you. Again, I highly recommend that take it seriously, study hard, go through examples, everything. What is it? Web work is important to go through the examples. Lectures are important, and class discussion. I gave a lot of examples on that, and also, of course, Excel is important too. All right. Good luck to all of you. All right. I'll see you on Wednesday.